Today, in the next hour or so, I will focus on the geological mapping of Mars. Actually, I will focus only on sedimentary deposits, because sedimentary deposits are a sort of unicum at least in the inner solar system, of course, with the exception of Earth. I will start with some basics of Mars very quickly, and then I will switch to why sedimentary rocks and environments are important, and which are the problems and peculiarities that we need to address in order to study and to map, first of all, them. I will focus on stratigraphy, which actually is important not only on Mars and not only on sedimentary deposits. And then at the end, I will show some example of fluvial casting systems in some way in preparation of the hands-on on Jet Zero later on. So this is a sort of family portrait, so to say, with some planets and satellites. Mars is here, as you can see, is definitely smaller than Earth. You would need 6 and something Mars to fill the volume of Earth, which leads to the fact that the gravity is just more or less 38% of the one of the Earth, which is one of the reasons why, not the only one, but one of the reasons why the atmosphere is much thinner than the one of the Earth. Then Mars orbit has obliquity like the one of the Earth. Mars has seasons. The interior structure has been addressed by the InSight mission, which was active until more or less a couple of months ago, which used S and P waves from Mars quakes in order to derive the thickness of the crust, which was understood to be 20 or 37 kilometers, depending on the case, much less than expected. The mantle is about 1,560 kilometers. But what's probably more important is the core, because the presence of an inner core was suspected, but no evidence have been found so far. If we have a look at the global physiography, Mars is characterized by a sharp dichotomy, a sharp transition between two zones. I should actually mention that this is a color code topographic map. The blue areas are the lowest, and then green, yellow, and red become topographically higher. So the whole planet is roughly divided in two, with the southern part, which is more elevated, more cratered, called the highlands, and the lowermost part, which is lower elevated and with basically very few craters at the lowlands. The transition is sharp almost everywhere, and it's called global dichotomy for this reason. Just in this area, in Arabia Terra, the transition is very gentle. We maybe should notice the presence of this huge volcanic continent, or province better, which is called Tarsis, with many volcanoes, including Olympus Mons, which is the highest volcanoes of the solar system. I would say, iconic fracture zone of Valles Marineris, plus we have huge basin derived by impact craters such as Hellas, Argyll, and Isidis. And then we have another smaller volcanic province, which is Elysium. This is very roughly the physiography of the planet. Mars has also, we should notice, also polar caps, which are seasonally varying. I was mentioning that Mars has seasons. They are mostly formed by water ice and some dust. Then there is a seasonal cap, very thin, formed by carbon dioxide, but the water part, the ice, water ice part is if not the largest reservoir of water on the planet. Speaking of stratigraphy, Mars, okay, this is Earth stratigraphy, this is Mars. Stratigraphy is divided, sorry, my mouse dropped and since then it became anarchic. Is divided in 3 periods, Noachian, Hesperian, and Amazonian. The Noachian last until 3.6 billion of years ago, Hesperian 2.6 billion of years ago. Then these periods are subdivided in epochs. There is a pre-Noachian period. We know very little about that, but we suppose that the dynamo was active and the geomagnetic field was present during that period. Most of what we found in the highland was deposited during the Hesperian and Noachian and Hesperian times, while the lowlands are mostly Amazonian. If we go in the details of the geological processes, of course, the volcanic processes are by far the most important, also from the volumetric, I would say, point of view. But sedimentary processes, including valley networks formation, outflow channels, related canyons, but also weathering, and of course erosional rates, and also sulfates, are largely confined within the Hesperian in the very first period of Mars geological history. Still, I mean, some processes, some sedimentary processes are active even today, very minor, but we have accumulation in the pole of the polar layer deposits, which are basically a mixture of ice and dust. And we have gravitative driven processes along the slopes, plus the atmosphere is thin, but thick enough to allow sands to be transported in dunes. So dunes are active, have been shown to be active even today. Why sedimentary rocks are important in Mars geology? Of course, they reflect surface processes, which in turn allow to, so to say, open a window to understanding which environments these processes were formed, in which climatic conditions, and so as a consequence also to what was their evolution through time and how the global condition changes, the global condition through time changed. This, of course, has implications in the climate, in the evolution of climate through time, possibly in the evolution of life. The last rover missions are especially addressed to that, and of course to all the resources which can be related to sedimentary process or sedimentary process, and maybe interbedded also with volcanic processes. There are two large group of sedimentary environments which have been proposed on Mars, detected on Mars, clastic sedimentary environments, which results from initial weathering and erosion in a source area. Here that we have transport by gravity, ice, wind, and or water, deposition somewhere along this path, and diagenesis to become from sediments to sedimentary rocks. In this case, this kind of deposits are alloctonous because maybe they are deposited somewhere here, but they originate from a source area which is here. Then we have chemical depositional environments. In this case, the high rates of evaporation lead to the precipitation directly inside the basin. So these are autochthonous deposits which are formed in the very same basin where we found them. Then some possible relation with plastic depositional environments here in the basin margins are also possible. This is not a super recent image actually, but still it gives you the idea of how much sedimentary deposits are widespread on Mars, because we have this is just the indication of sedimentary deposits found on high resolution images, white high rise, black mock narrow angle, and you see how they cover most of the planet. Combining the presence of sedimentary deposits, their morphological assemblage, their age, using crater counting technique, as you saw in the next day, and of course the mineral content derived by the CRISM omega emission. Beatrice was speaking about this, I guess a couple of days ago or 3 days ago. It was possible to derive this sedimentary mineralogical evolution stratigraphic scale, where clay-bearing deposits were dominant until the mid-Noachian, suggesting water-rich condition. Then these clay-bearing deposits started to be interbedded with sulfate-bearing deposit during the late Noachian and the Hesperian, suggesting that condition with an increasing water limiter content, and then during all the Amazonian, these conditions became water limited or hyperarid better. This is very of course a first scale understanding. Mapping these sedimentary deposits is important, is actually the only tool to assess, of course, the geographical distribution of the given unit, but especially the only tool to assess the vertical and lateral relations between the different units. So it's the prerequisite to associate units or landforms which are laterally coeval. So this will lead to the possibility to reconstruct not the single landform, but entire landscapes, which means environments and their evolution through time. I will go back to this point later on. I hope it will become more clear. And of course, this process will lead us to understand which control the evolution of the environments. I would say first the presence of an environment in a certain place, in a certain location, and then its evolution through time, and the climatic changes which characterize this kind of evolution. Of course, this has implication on the habitability potential. So told, we have to say that the mapping Mars has problems and peculiarities. I must say that most of these points are actually not only for sedimentary rocks, and sometimes not even just for Mars. First of all, scales are instrument dependent. It's true that even on Earth we have a geological map of different scales, but when I go in the field, I see things and I decide a kind of scale that I want to use for my representation, depending on what is my goal, science, technical, whatever goal. On Mars, no. Mars, on the planets, the scale of my geological map will be dependent on the image that I have available in that specific place. Then we have, this is a remote sensing, totally remote sensing method with no or very limited ground truth, because we have very few rovers on the ground. On Earth, normally we can maybe have ground truth, not in all of our study areas, but at least we can tie our analysis with some observation on the ground in some specific important points. Another point is that we have very limited information on rock composition. We have what are some kind of hints on mineralogical content, but we do not really know what rock we have in our areas, which, I mean, somebody might claim that we cannot even speak about geological map, because geological maps technically on Earth are something which is based on the lithological content of the rock. On the other hand, we have a relatively limited amount of weathering, which implies a good preservation of morphologies, even in the deep geological time, unlike Earth. This is one of the reasons why the traditional approach in planetary mapping has always been chronostratigraphic or geomorphological rather than, I mean, geological as we intend it on Earth. Then we have the problems of scale. I was mentioning something, but also of equifinality. I will go back to this in a second. Problem of scale. Here we can, with this resolution, we can recognize, of course, these images are taken from the same place. Here we can recognize the presence of a fan-shaped feature. We can, I mean, just realize a geomorphological map. If we switch here with a better resolution, we can distinguish much better the morphology. We can recognize that actually is not one single landform. There are different fans superposed, there are lobes, but we can also see that there are two different geological units, a light tone one here and a darker tone one here. If we move here with an even higher resolution imagery, we can not only observe the characteristics of these two units. So this one, this light tone one is bedded, for example, but we can also evaluate the kind of transition we have between these two units. So we can switch to a different kind of geological representation. When we map, we need to take into account that, of course, we need all the data sets because we want to observe all of the characteristics of the units. And of course, we want to be prepared for the following scientific interpretation after our map is ready. But we have to remember that our map should be consistent throughout all its extensions. So if we do not have, for example, such a data coverage, throughout all our map, we cannot use this map again, to realize this data to realize our geological map. We must keep our representation consistent throughout all our study area. Again, problem of scale. Another point related to the problem of scale, and again related to the fact that we have very few in situ data. Geological analysis has a first part, which is a geological context analysis, and then we move to the detailed observation measurement. The geological context, this is Earth, this is Mars, can be done with similar scales on Earth and on Mars. But if we move to the second phase, the phase of the observation of the measurements, here we are in Dalol in Ethiopia, we observe some mounds. This is Mars, mounds more or less the same is similar. We have this polygonal pattern, more or less the scale is similar, but then on Earth we can move even without microscope. We can move just with sample by hand. We can observe, for example, that these rocks are made actually of crystals, so are crystalline rocks, while on Mars we have no idea of whether these are, again, crystals, precipitated crystal, or clast. So we have no idea whether rocks are clastic or chemical evaporites. Then we have the problem of equifinality. Equifinality means that similar effects may be generated by different combination of causative processes. And this is a very, very important always in geology. Same mounts as before. They might be formed as erosional remnant. So they might be even not be a depositional feature, but erosional feature. Or they might be formed as pingos, so in a glacial settings, or as mud volcanoes, such as here, or as spring mounts. And I'm not even mentioning all the possible volcanic or association between volcanic and sedimentary processes. So the study of this landform will stuck us at some point. So how can we cope with that? How can we go on? The only way is to integrate data and define a geological context. So switching from the interpretation of the single landform, for example, the mound before, to the associated landform, mounds associated to other layer deposits or whatever, in order to mutually constrain the interpretation. In order to do this, it's important to evaluate the unit lateral and vertical distribution in order to associate landforms which are coeval. In order to do this, we need to realize a geological map and evaluate the stratigraphic relation, so the basic geological work. Only then we will move on. We can move on with the interpretation using the multiple working hypothesis approach, which is beautifully defined by Baker in 2014. I strongly suggest all of you to have a look at this paper, and analog study. So you start with the formulation of genetic hypothesis about your study area, following the consequences of each of these genetic hypotheses, and then testing this hypothesis to try to understand which is the one more consistent with your data. So this leads to stratigraphy. I guess you had already, Monday, some words about the importance of stratigraphy, which are the tool to order rocks and time. The principle of stratigraphy were defined by Stein already in 1669. We have the principle of original horizontality, of superposition, lateral continuity, cross-cutting relationships. These principles basically are the basic tool to order the rocks of a specific area with respect to time. So, example, here we have a geometric reconstruction of a possible study area. We have a crater margin, for example, with some rocks which were accumulated by the impact, then the accumulation after we have the accumulation of some evaporites that were slumped. Then all of these succession were cut by this channel, which later on deposited some fluvial material. After all of this, the entire succession was draped by Aeolian dust, recent dust deposits. This representation allows you to estimate the relative timing between the different units. If you want to express this information relating to time, you can use this kind of diagram, which lose the information about the mutual geographic relations between the different units, but gain the meaning of these units respect to time. So you will be more aware of the time which is missing between different units, and of course when the time is continuous. For example, the deposition of the evaporites of coal continuously. Then there was sometimes before the incision by the fluvial channel, and from this kind of diagram you will be able to see clearly that these two phases belong to different phases in the historical evolution of geological evolution of this area. Just to give you an idea of the missing time, this is, again, sorry, I should buy a new mouse. This is an unconformity on Mars. Unconformity means that there is along this surface sometimes which is not represented, sometimes was never deposited, sometimes was lost by erosion. So we have the deposit. This is taken by Curiosity in Gale crater, by the way. These deposits are this altitude here, and we have this other altitude here. In between, sometime is missing. In order to try to explain better this concept and the importance of this concept, I will move to this Eberswalde crater and delta-like feature, which is also historically very important on Mars because it is considered to be the smoking gun proving the evidence of the existing of water stable on the surface of the planet for a geologically significant amount of time. Before this image, which came out in 2003, many people suspected that water on Mars had been present only in quick outburst of water. Here, this is a classic, very classic, clear delta, which proved that water was stable along the surface for a long time. And this is a detail of this delta with, meandering distributary channel. These are distributary channel. This is a beautiful meander with a chute cut off. These are distributary area. This is the delta front. But olivine was found in correspondence of this delta. So somebody claimed if there is olivine, which is very unstable with water, that cannot be water at the same time in water, I mean in a fluvial deposition environment. But if we go closer in this image here, we observe that first of all, we have two geological units, a light tone unit and a darker tone unit. The light tone is bedded, the darker tone is reworked by this Aeolian bed form here. And if you look at the contact actually cuts some of the light, which is drawn very poorly by me here, but by the way, it cuts some of the light tone layers before. It means that there is a non-conformity between the light tone unit and the dark tone unit. It means that these two units belong to different history, different part of the geological history of this study area. And in fact, if you look at the A2 abundance map here, we saw that there is almost no water abundance here in correspondence of the dark tone deposits, but there are in correspondence of this of the material comprising the light tone formation, which is the one related to the deltaic evolution. So the olivine-rich deposits lies above the disconformity, and we have two different histories, which geological histories of this delta, which should not be confused, which should not be mixed, I would add. Since I was speaking, and I am about to speak more about beds and layers, I should tell you something that it's a sort of premise to all of these kind of arguments. If you look at this, for example, how can we be sure that this is not a bed, but actually stacked a number of superposed similar bed, which resolution, which are too thin to be observed by our resolution? Actually, there is no way to know that. So it would be technically more proper to speak about bed set instead of beds. Still, I mean, this is just a terminological problem. It's not a big deal. It's very okay to call these beds or layers. It's not a problem. The problem is that you should always remind of this problem of resolution. So if you compare these beds to other beds, you should always use similar resolution, the same resolution actually, like they did in this properly in this paper, because otherwise if you compare images with different resolution, you would compare something which is actually uncomparable, and your results will have no real meaning. When you speak of bed, now let's call them bed or layer to be more simple, you should always pay attention to their termination. Terminations are very important in this, when you can observe them, of course, because they tell us something. Let's start what we already saw, truncation. If one bed is truncated somewhere, it was eroded, this means that, again, like we saw before, sometime it has been stripped away, some rocks, and of course also a corresponding time it has been stripped away, it has been eroded. So we have a break in the sedimentation. If we have horizontal layers which goes and hit against an inclined surface like this here, we have something which is called onlap. The name is not so important. What is important is that this geometry suggests that the basin is infilling, and this is important. Instead, if we have horizontal layers which pass to inclined layers, and then they go and finish again the surface in this with this geometry, we have a geometry which is called off-lap, the entire geometry. This way in which they hit the base is called down-lap. The inclined beds are called clinoforms or forests. I know that I'm telling a lot of words, but words are not so important. The important is that this geometry means that we are moving the sediments in this direction to fill the basin in this direction. It means the basin is prograding. We will see this in G0. If we do not have the flat part of this geometry, we will have top lap. So it means that we are just moving in this direction, and we have no growing, vertical growing of these beds. Let's have a look at these geometries on Mars. This is this is an example of truncation. We have these nice light tone beds which are cut here, and a new units, these dark tone deposits, are deposited on top. This is an erosional truncation. It means that there was the sediments were deposited, then eroded, then the deposition stopped, then there was erosion, and then a new unit occurred. So some time is missing here. Here we have horizontal beds which are embaying this older, this is actually crater margin. This is an onlap. In section, the representation, the geometry is more or less this one, and maybe it's better and more clear here. This is an onlap. This is a crater margin, and these beds are moving against the crater margin in this way. They are infilling our basin with this fashion here. Example of downlap directly from Curiosity. These are the beds below, more or less horizontal, and these are clinoforms which are prograding in the basin and hitting the surface. You see this geometry, this boom. It means we are moving deposits in this direction. Other point which can be important, lateral transition. If we have lateral continuity, if we are so lucky to have lateral continuity, we can say that deposits are coeval. Coeval, it means, for example, here we have mounds and layers here. And the question was, are these layers post-dating, predating, or contemporaneous to the mounds? And the answer is here. We have layers from the mounds which continue outside of the mounds in continuity. It means that these two environments were coeval. So they were deposited at the same time, laterally equivalent. To form sedimentary rocks, we start with the processes, which, for example, here, this is aeolian transportation cluster are transported by siltation, reptation, insubstantiation. These are the processes. With time, processes lead to the formation of landforms. This is a dune, for example. And here there is an important passage, because the landforms are short-term features on Earth, but long-term features on Mars, which means that they are preserved in the deep geological time, unlike on Earth. Then, with more time, we have the formation of deposits. These are dunes accumulated through time. Cross-bedding is related to the movement of these dunes. But to see, these are long-term features both on Earth and on Mars, but in order to see them, we need erosion and exhumation, which is not so trivial in a planet such as Mars. Ideally, mapping landforms, it means mapping geomorphological map. Mapping deposit means creating realizing a geological map. Example, this is a geomorphological map. Again, the Eberswalde crater that you saw already. Here we distinguish between delta, the distributary channels, interdistributary areas, distributary channel. This is the delta plane in shades of blue, delta front, pro delta. This is an interpretative map because we map this unit according to what we think is there. We thought it was the genetic origin within a delta. Geological maps on Earth have the meaning to be as objective as possible instrument. So they are based on lithology, which is the most objective parameter that we have. Of course, on Mars, but in general on the planet, this is a problem because we have no or very few information about lithology. So how we can be, between brackets, objective? We can try to find some characteristic which can be, again, between brackets, objectively described. For example, the color, the texture, if they are layered or not, if they display sedimentary structure, and we should do this at all scales. And then associated this with morphologies intended not with the interpretation, but just as forms, as for example, they are sharp, they are mound-like, this kind of stuff. And of course, the stratigraphic position within the succession. So this is the map, the very same area, no, the Eberswalde crater, but a geological map. So as objective as possible. We have a substratum, which is this one, the older one. Then we have a light tone unit, a layered member and a non-layered member, covered by what we call the mantling unit, by a dark tone unit, and then aeolian bedforms. Between the substratum and the layered unit, the light tone unit, we have an unconformity. Another unconformity is the one we saw before between the light tone unit and the dark tone unit. So, okay, but before starting any kind of map, geomorphological or geological or whatever map, you should start from a reference area. What does it mean, a reference area? On Earth, when you start to perform a geological mapping, first you go and look to a physical place, which is called stratotype, where all the characteristics of a given unit are nicely exposed and are very well described in some papers. So you will be fully aware of what you are going to do. You will have a clear mind of your units before starting to map. Then mapping will be easy. This is something that it is actually very important, because if you will do carefully this part, the second part, the mapping part, will be really straightforward. You should do this again before starting to mapping. In this way, basically, again, this is always the Everswalde crater, starting with low resolution image. This is HRSC unit. We want to describe the light tone deposits. With the HRSC, we can say that they are light tone, that they are associated to this fan-like feature, and they are, so fan-like feature, it's not interpretative, it's just the shape, and they are present only in correspondence of this feature. Then we move to CTX resolution. We can see actually that this unit, this light tone unit is ragged, that it is layered very well. It overlaps here this other unit, the one that we call stratum. In the other map, you see boom, boom, boom against this unit. And it is covered by the dark tone deposits here. If we move to high rise, we can say even more, because we can say that this unit is the light tone beds are disrupted in the polygonal, this polygonal pattern, and we can see that the contact between the light tone unit and the dark tone unit is unconformable. Of course, the ideal would be to, in one future, to have some points in which ground truth made by a rover, or even better, made by humans, could tie our geological map. This is a beautiful, I would say also historically important example, because it's one of the first stratigraphic sections done by a rover. This is opportunity. Now, very quick glance to fluvial-lacustrine deposition environments on Mars, since I mean, we are going to work on Jezero crater. Fluvial-lacustrine deposition environments are made of different, I would say, sub-environments. I will speak about in a very non-exhaustive way of alluvial fans, valley networks, and channel deltas, and the lacustrine systems themselves. First of all, premise, sedimentary basins are a low area in the crust in which sediments accumulate. On Earth, the basin forming processes are almost entirely linked to plate tectonics, not only, but almost entirely. So the subsidence is provided by plate tectonics, which basically creates our basin. On Mars, the most important basin forming process is impact cratering, not only, but mostly. Alluvial fans. Alluvial fans form at the break of a slope, for example, here, where the topographic slope change, which leads to the position at the edge of a floodplain. When we have many alluvial fans just opposed, we have a bahada like this one. When the break of the slopes do not occur in a floodplain, but in a standing body of water, we have a fan delta. So river channel, bedrock channel. Bedrock channel means that it is cutting rocks. It is not leaving sediment, but it's just cutting rocks. Another kind of alluvial fan, which is a little bit peculiar, is the terminal fan. In this case, the loss of competence is not related to a change in the slope, but simply to loss of to evaporation and infiltration of the water. This is, of course, typical of arid climate, when water is in some way leaves the system, again by evaporation or infiltration, and you have deposition of because of that. This is an example of an alluvial fan on Earth, and this is an alluvial fan on Mars. This is Holden crater. Valley network have been represented in this map. All the valley network, you see how widespread they are represented in red. In blue, you have the two. You might know that there is a big discussion about whether Mars had an ocean in the northern lowlands or not. This is still a matter of discussion. The two shorelines which have been proposed are this one with two different shades of blue, and I must say that they fit pretty well with the distribution of the valley networks. This is an example of valley networks here, or single valley here. What it is interesting in an alluvial plain, so where this is the river, the fluvial channel, and laterally there are the overbank deposit, which forms when the water is not confined anymore in the channel and it just gets out, forming first of all the levee immediately after it is out, then the floodplain deposits, and in the case it breaks the levee, it forms this form that is called crevasses plain. These overbank deposits, with maybe some exception of the crevasses plain, are definitely much finer grained than the channel deposits here, because they are formed only, most of the transport, the higher energy transport, is confined within the channel. So it means that they are very much easier to be eroded. If you look at this sketch here, this sketch was developed on Earth, because this is a very classic process. We have a channel which is made of sand or even gravel, floodplains or overbank, which consists mainly of clays. After this history is finished, so the alluvial environments is for some reason is abandoned, erosion starts. The erosion of the floodplain deposits, even only by wind, is very efficient. The erosion of the channel, which is coarser grained, is much lower efficient, if totally inefficient. So as a result, the channel will result as an exhumed form, so it will stand higher. That's why it's called exhumed in the literature, because it stands taller because the material here has been eroded. You will see in the literature also the word inverted, but inverted channel is less proper. Exhumed channel is more conform to this process mechanism. This is an example of a exhumed channel on Earth. This is Utah, but there are beautiful examples in Algeria, in Spain even. It's quite a classic process. This is a beautiful example of exhumed channel on Mars. This is Aeolis dorsa, and this is a meandering channel which relative floodplain material has been partly taken away, partly eroded. I was mentioning before that it's very difficult to find deposits on Mars for many reasons. But in this area, which is not far from Hellas Basin here, along this outcrop, Salese et al., they were able to find actually stacking channels, superposed channels. For example, you see here, these are meandering point bar deposits, while these are stacked deposits of channel. It means that here the fluvial sedimentation was persistent really for a long amount of time, and with geometrical characteristics which are totally comparable to the one we have on Earth. For example, this is the similar example from Earth. This is stacking channels, superposed channels. Then when finally the alluvial system or even the bedrock river enter a standing body of water, we have the formation of a delta, which is a fan delta if the river was a bedrock river, so coming directly from the mountains, or a delta when it was an alluvial river. So if we have an alluvial plain before the delta deposition. Delta are distinguished have three major parts: delta plain, a delta front, where the delta plain is totally emerged, or most of it is emerged actually. The delta front forms where the fluvial deposit starts to interact with the standing body of water. And then we have the prodelta, which is below the wave action. And okay, again, the Eberswalde is a classical example of delta deposit with delta plain, delta front also here, and prodelta deposits. And of course, Jezero crater. Jezero crater is a deltaic system. We will look at it later on. This is an image from Mars Express, and this is one paper which was done on Jezero, where they could observe Gauge et al. They could observe very well the geometry of the beds in the delta front, and they observed some horizontal beds here and clinoforms downlapping on top of this layer, so showing a progradation. So the deposits were delivered inside the basin during this phase of the deltaic evolution. And this is one of the first images taken from Perseverance. We will hopefully know much more about this. We will have ground truth actually hopefully in a while. Casting systems are more difficult to be detected because coastal systems in lakes are relatively poorly developed, and this is true even on Earth. And in any case, coastal deposits are easily eroded. That's why it's so difficult to establish whether the famous Martian Ocean existed or not, because these deposits are the first one to be eroded. So we don't have many signs. We can have some terraces, which are the remains of these coastal systems, but the most important geomorphological element is the flat blazing form. And that this is an example from Gale crater, as seen by Curiosity, the floor of a casting system. So very quickly, sedimentary deposits are the key to understand the environmental and the climatic change. You should decide your scale and the type approach of your mapping depending on what you want to do, what is your science goal. In any case, pay attention to stay consistent throughout the whole map. First, describe the units, then start to map, and always keep attention to stratigraphic relations between the different units. Okay, I don't think I need to go into more detail because I told this already, and I think I was even speaking too much. Thank you. Thank you.